So just a couple of words about the ACT, Advanced Concepts team. It's basically the think tank of ESA, and we're basically looking at technology that can potentially play a role in space exploration in the not so near future. So our horizon is like 20, 30 years into the future. So because ESA works with these timelines, just like NASA, so missions last a long time. So we kind of have a long horizon to evaluate technologies, and as part of this mandate, we are a bit of an outlier at ESA. So we do research, whereas ESA in general is not a research organization. So we have projects on anything from biomimetics to natural language processing, to continual learning, fundamental physics, biologically inspired AI, megastructures, mission analysis. You get the idea. It's like everything that you could imagine. Nothing is taboo. Nothing is too out there, too wacky. And as part of this diversity, we also, of course, do research on neuromorphic, because this is an emerging technology that's actually very interesting to ESA. So if you want to learn more, you can visit the website and look at our projects. So you can get a better idea of what we do. I'll just briefly outline the sort of the motivation for doing neuromorphic research at ESA. Why is ESA interested in neuromorphic? Well, space is really uninviting for humans, as we all know, so we have to rely on machines. And some examples here of recent successes and failures. So the Ingenuity helicopter was the first machine that flew on another planet. It's a fantastic achievement. And of course, some failures, like landers that were probes that were meant to land properly on the moon and tipped over and so on. So there's a great reliance on autonomy, or let's say autonomy will play a greater and greater role in future space exploration. And of course, since power budgets are tiny and there are in many cases very requirements for very low latency, like during descent or obviously when flying, you have to have very quick reactions. This is where neuromorphic is very interesting. So being able to perform all of these wonderful feats of engineering with autonomous machines, but with a tiny power budget, and in a radiation, in a hazardous environment. Let's say there are great sort of promising, there's very promising indications that neuromorphic chips and sensors are very resilient to radiation damage. So this is the sort of the motivation, and the question is, how can we enable this? So we have some activities, even outside our team. People are already starting to look into, let's say, event cameras, neuromorphic chips like the Akida. I'm not going to get into a debate about whether Akida is neuromorphic or not, but let's just say that the way it's marketed. And of course, Luigi and so on. So there is great interest in this space. So I'll give you a quick overview of some projects that we have in hope that you might pique your interest. And so I will start and end with projects that I am leading. This empath model is basically a new spiking neuron model specifically designed for continual learning. What we're testing it on is drone control for now and optical flow estimation. So on board for optical flow estimation, with the aim to transfer, sort of transition the drone control to let's say satellite control or in general some sort of spacecraft control. So this is one line of research. We have a few activities in the middle that I'll mention, such as burst-driven control, continual learning, learning with memristors, and so on. And I will end with another project that I'm leading, also with the one and only Julia D'Angela. So we're working together on this tool called Perception that I will outline in a bit more detail. Sorry. Okay. So briefly about the empath spiking model that we're working on for drone control. So the whole idea behind this is to have a sort of a plug and play neuron for spiking networks, where you don't have to fiddle with and tune a million parameters. You have one neuron that you can train in any situation, even in a continual learning situation, with the idea that it will adapt to whatever input you're presenting to the network. It's a spiking neural network. Actually, the neuron doesn't have to be spiking, but it can also be spiking. It's a very generic neuron formulation sort of model. We have it's work in progress, but I don't know if you can see this. This is a drone racing sort of model where we apply a constant bias to emulate sensor error. After 4 seconds, so 4 seconds into flying, we introduce this sensor error. And you can see that the original, what we call GECNets, these are tiny little networks, control networks that can control the drone. They're actually on board. The original network fails to take that into account. It sort of diverges, the trajectory diverges, and it can no longer, the drone can no longer pass through the gates as intended. And the empath controller is actually gradually adapts to this bias, to this sensor error, and returns to the original trajectory, which is obviously very useful. I've left the QR code here for the page for GECNets, which is a very prominent line of research in the team, if you're interested. And another work in progress with the empath model is continual learning for optical flow estimation. So optical flow from events on the fly. This is kind of early research, so I don't have much to show here, but one plot where we basically tested the leaking integration and the empath model. It turned out to our great surprise too that the empath model reached a lower error, and it actually learned faster than the leaf model. So stay tuned for more on this research. We have also someone working on memristor technology, so developing um, basically modeling neural networks with part or even fully implemented in with memristors. For those of you who don't know what a memristor is, it's a fundamental circuit. It's basically a resistor with memory that remembers its resistance depends on the current that has the history of the current that has flown through it. So we're investigating the applicability of memristors for onboard learning. So memristors are naturally radiation resistant, have low latency, super energy efficient, so on. And they're analog, so all the benefits that come with the memristive technology also introduce issues like a lot of noise. These memristor cells that you need to use to implement the network, that they eventually become read-only, so you cannot learn after a while, and so on. But it's still a rather promising avenue. I will also leave this QR code for. By the way, if you have any questions or comments, if you want to know more about any of this, just stop me, or we can talk afterwards. Just reach out. I'd be happy to expand on any of this. Another very recent activity that we have is an Ariadne study, which I've put the URL here for you to take a look. So basically a mechanism for collaboration with universities, between ESA and universities. And so we have this Ariadne study right now on burst-driven continual learning, where we're looking at bio-inspired learning rules that can be implemented again on board. Well, because we were working with this lab at TU Delft that's basically specialized in drones. So this is specifically for continual learning on board drones. But as I said, this is transferable to other flying or other machines. So the idea here is to use spike bursts as a proxy for the gradient in a network. So this is an early work that we're we don't have concrete results yet, but it seems that the bursts indeed can approximate the gradient and be quite competitive with the gradient descent even. So this is an exciting promising early result. And we also had an activity called Neurosat, using neuromorphic processes in SATCOM systems, where this was actually quite a long study with the goal to assess the use of neuromorphic hardware, the promise of neuromorphic hardware and software for SATCOM, with applications like digital beamforming, interference detection, congestion prediction, and so on. And you can look at the website for the Neurosat activity. It is up and still quite active research going there, in collaboration with the University of Luxembourg, if I'm not mistaken. Um, so one of the main interests in neuromorphic technology in general, but specifically perception, is vision-based landing. So ESA is very interested in vision-based landing. So landers now use a lot of equipment that's very bulky and heavy, not very accurate. So this image that I showed of the probe that's tipped on its side, well, maybe we can avoid situations like this, because this hundreds of millions of dollars are at stake, and things can go wrong at any point. So vision is a very sort of interesting. So vision-based landing is a very interesting sort of track for ESA, and specifically because of the now recent interest in event-based cameras, event-based vision for navigation and language and landing. So this is what is the problem here? Well, we haven't had any. We don't have any real data from a mission to landing mission somewhere, maybe on the moon or Mars. We haven't sent an event camera uh, anywhere beyond the ISS. That there was one study where they sent an event camera and acquired some data from observations, like Earth observation data. But these are single examples. So what we want is to be able to study the ability to maybe, or to see if we can match the performance of landing algorithms. So this uh, idea that you can create an optimal trajectory and follow it with a vision-based system to land. So can we actually do that with events? Well, there is a great piece of software that was actually commissioned by ESA called Pangu, planet and asteroid generated. I'm not really sure what Pangu actually stands for. I think it's planet and asteroid natural scene generator or something like this. So what you can do is generate these photorealistic sequences of well, it's essentially video at any resolution you like, because it's rendered with great fidelity and extremely flexible configuration. So we can render these scenes as if a lander well, a probe is following an optimal trajectory. So we can specify a trajectory, and it will render the scene as if as viewed from the spacecraft landing, and we can then convert this scene into a motion field and also generate synthetic events from that scene. So this pipeline that we developed actually in the team is available. So modular the Pangu license, it's all open. So if you want to use it, please do. And yes, so the idea here is to investigate whether this last version of the data, so the synthetic events, can be used for optimal descent and landing. Obviously, this is also useful for was kind of directly transferable to tasks like rendezvous. So two targets need to meet and sort of attach to each other, because it's the same principle. We need to match the velocity and the rotation speed and so on, and then finally touch them. So okay, I was a bit of a sudden shift in focus. Um, we we're interested in vision in general and event-based vision, but what uh, what do we actually want to achieve with bio-inspired vision? Okay, so as we all know, the retina computes all sorts of features and types of motion, and so before even sending, so the spikes that are generated by the ganglion cells are very informative. So um, they don't just transmit the fluctuations in brightness, but they transmit a whole lot of information that the brain interprets further upstream. So, of course, retinal models that we have, like the early silicon retina, this retinamorphic hardware. So this analog model that works very nicely, modeling certain features of the retina, like adaptation. So this is from Misha Mahovold and Carver Mead's article, famous, where they demonstrate that this circuit can actually behave like a retina, even down to the sort of the process that generates an after image, staring at an input image, and adapting to it, and finally, when we substitute the image for a white sheet of paper, we get this after image, which is the negative. So they demonstrated that this is all possible, and of course, fast forward a few decades, and we have the state of the art right now, event-based cameras that sort of follow the envelope of the brightness and produce events, on and off events, as the brightness fluctuates at individual pixels. But the problem is here that this very ambitious early research on modeling all the features of the retina sort of well, for better or worse, sort of got simplified, I think, into a more compact version of the hardware that we now have, the event-based camera, and it's certainly very useful. However, we're still missing this. We're still missing this richness of information that the retina provides at the exit. So when we generate a spike, what does this spike mean? Or maybe a spike train or a burst of spikes. What does it mean? Does it mean that something moved in the visual field? Does it mean that an edge is present, and so on? None of this is available at this moment with the current hardware, and of course we have the software models like convolution, of course, in convolutional networks that applying a kernel to an image to extract certain features and so on. So we can sort of simulate various features of the retina in software, not in hardware. Even this is kind of limited in sort of what you can do with convolution these days. So at this point, I am going to mention the project that Julia and I are working on. It's called perception. So the sort of that will give you a sort of an overview of what the project goals are. The goal is basically to develop a tool for biorealistic modeling of the retina. So we know that there have been various attempts at modeling the retina in hardware and in software, but this biorealistic level is I think still elusive, and so this is kind of the motivation for this project. And the main sort of the base for this for this tool is it's basically a software tool. It's for simulation, and the idea is that if we can demonstrate that certain circuits, certain retinal circuits are feasible in terms of yes, we can create them and they can give us useful information for, based on what processing they perform. Then we can maybe have a good case for arguing for creating a hardware version of these circuits, maybe a dedicated circuit. Maybe it doesn't have to be a generic sensor. Maybe it can be a circuit that can perform a certain very specific function, like extracting or suppressing ego motion, or I don't know, attention, or you name it, whatever processing the retina is capable of. If we can demonstrate that certain circuits are capable of performing these operations, then we can argue that it may be beneficial to create hardware that emulates these circuits. So at the base of this project is an observation that convolution as implemented these days in deep learning libraries is actually a very limited, as I said, limited operation. So okay, how is convolution implemented? We basically unroll individual patches of the image into columns. So these columns correspond to patches the same size as the kernel. We roll the kernels into rows, and we convert these into two matrices, multiply them, and we have our output. So what is the problem with this? Well, we cannot model any complex structures as we see what we see in the retina, like center surround fields. We cannot model log polar distribution of cells with foveation. We cannot model eccentricity dependent receptive fields, and so on and so forth. There is a reason for evolution being what it is, why it's implemented this way, because it runs very well on hardware like GPUs. Because GPUs like everything to be continuous and sort of fixed and predetermined, but we don't want that. We actually want to be able to model arbitrary circuits and complex receptive fields, complex responses, inhibitory and excitatory inputs combined in certain ways. So here is where here's the essence of the perception tool or framework. And I'm not really sure what the right term is yet. Something that I call sparse convolution. What is sparse convolution? Well, I will briefly mention. In contrast to what we do in normal convolution, where we unroll individual patches of the image, the same size of the kernel, we unroll the entire image into one giant long vector, and we look at the segments that correspond to the kernel that we want to apply. So where are these segments? Well, they're not continuous anymore in memory, but what we can do is take the kernel that we are applying and unroll it into a sparse row, into a sparse tensor. So each row of this sparse tensor is going to contain one copy of this kernel that corresponds to a different location that needs to be convolved in that image. So as we continue the process, we can perform exactly the same type of convolution as we can with the tools available to us now, except that we can also implement any other complex receptive field and sort of cell organization that we like. So just with this simple inversion of the convolution operation by using a sparse tensor, this actually gives us the superpower to model any kind of receptive field that we like, including log polar, sparsely distributed cells with the log polar distribution, or eccentricity dependent receptive fields, and so on. So this is kind of at the center of this new tool that I'm working on in collaboration with Julia. So we have implemented all the retinal layers, can emulate and successfully demonstrate that this works. And of course, being a PyTorch library, it's a GPU friendly, so you can use it with your PyTorch tensors. So of course, it's work in progress. Software is never finished. So implementing arbitrary temporal dynamics and let's say saccades, saccadic movements, it's actually also possible to implement that with by shifting the location where the fovea, basically the center of the fovea, and expanding from there. It's actually quite straightforward. And it is an open source project, or at least will be shortly. So contributions are welcome. If you're interested in a tool for simulating arbitrary retinal circuits, this maybe it. And of course, why are we doing this? This is interesting for things like egomotion, subtraction, attention, that are part of the Telluride sort of set of projects. And the concrete application that actually started this project in the first place, autonomous landing, specifically optical flow estimation. So implementing circuits that are actually only sensitive to approaching motion. So as we land, as you know, everything looks like is diverging. So as you look from above, the features are diverging and going in different directions. So a circuit that's sensitive only to approaching motion is actually extremely useful because it can eliminate the sort of the noise introduced by lateral motion or other types of maybe tilt and so on. So this is an extremely useful application. And of course, as I mentioned, if you have a generic framework for modeling retinal circuits, maybe you can maybe you can argue that creating a more sophisticated, dedicated hardware circuits is justified. So just to give you an idea of what perception can do right now, you can create, let's say, this is just an example. So a log polar distributed set of cells with eccentricity dependent receptive fields. You can even address, so to speak, so extract a certain portion of the cells, let's say a sector that corresponds to a certain direction of motion. Maybe you need to extract motion just in that part of the visual field. It would be very trivial by using features available in perception. So you can take these cells, for example, and apply further processing before feeding them into the next layer and so on. Same for, let's say, what I call rings. So these rings are also very easy to extract for applications like this circuit that I mentioned, the approaching motion detector. This would be very useful because everything in the visual field diverges and concentric rings get activated progressively as you approach the target. You can have non-uniform receptive fields, so these elliptic kernels that are oriented in a certain direction. Maybe it can be oriented at a degree of, let's say, 45 degrees, an angle of 45 degrees. Whatever filter, whatever receptive field you would like to have, you can implement that and create a custom class and just derive from the base classes and just implement your own kernel. Just examples of okay, for example, you can also implement multiple layers that take sparse input as well, take sparsely distributed cells as input. So, for example, this is an example of an amacrine layer, again, log polar distributed with receptive fields that take sparsely distributed bipolar layers as input. So each of these cells, I don't know if you can see well here, but the cyan dots are the amacrine cells, and each of them has a receptive field that covers just a bunch of bipolar cells, which are actually sparsely distributed. So all of that is available. Just a bunch of plots. Again, just an example of what you can do. Taking a static image as input, you can feed it into the pipeline, and let's say emulate the feedback from horizontal cells back to the photoreceptors. So we take the raw input, activate the horizontal cells, extract the feedback, and so modulate the raw input by this feedback, and feed it further into the bipolar layer. We can split the signal into on and off pathways, just like you observe in the retina, and onto the amacrine cells and ganglion cells and so on. So ganglion cells produce spikes, obviously. Again, all of these types of layers are customizable. If you take the library, you can implement your own, let's say, your own amacrine cell, or multiple types of amacrine cells, and build your own circuit and see what comes out. So hopefully this would be very useful. Yes. Oh, just a quick demo. I'm still struggling with visualizing this. So okay, Matplotlib is not the best tool for animation, let's say. So I'm looking for a better way to visualize the activation of the individual layers. But let's say this is a work in progress. So I hope that there we go. So an approaching motion that activates different layers. So in this case, this is at the top left. This is the raw input with the horizontal cells being activated in the middle, top middle. And on the right, this is the feedback from the horizontal cells. And the scaled input is in the middle on the left here. The two bipolar pathways, the two amacrine pathways, the on-driven and off-driven, and the ganglion layer. So this is really kind of a haphazard introduction to research that is happening here at ESA, and I hope I managed to pique your interest at least a little bit. And if you have any questions or comments, feedback, criticism, I'm open to it. Please let me know. Thank you.
Awesome. And so just a bit of background, I started off as an engineer, and then I did neuroscience for like 10 years. Yeah, this topic of neuromodulation is really close to my heart. And now that I'm moving into AI, I'd like to think about how AI algorithms can help us make sense of what these neuromodulatory systems might be doing, as well as how we might leverage them for algorithms. I'm giving this talk with Marco. Did you want to introduce yourself?
Hello everyone, my name is Marco. I'm a PhD student at Local University. Where I'm working on principally computing for AI applications.
So yeah, this topic of neuromodulation of LLMs has come up a few times in this workshop so far. And usually this has been in the context of hoping to mimic natural intelligence in some way, either for its ability to make adaptive decisions, take action in its environment, update its internal beliefs about the world, and as well as appropriately direct its attention to the most pertinent information, but just that's behaved. And all of this while doing it within a tight power budget. So we want efficient and accurate LLMs. But as we learned from Ivana's talk earlier this week, we know that this is something that LLMs don't always, they sometimes struggle to do. For example, in this case, the LLM failed to produce an image of a vase that didn't have a virus in it, as requested. So it either couldn't attend to the right information or got distracted in some way. And so natural intelligences have evolved mechanisms to address similar problems because survival depended on it. And they also had hundreds of millions of years of evolution to do it. So for example, during stress, the amygdala and hypothalamic networks inhibit cortical centers involved in higher cognitive processing to allow basic instincts to take over when you might only have a few seconds to live. And so this idea of brain-wide structural changes is similar to recent demonstrations from the AI community. So I'm going to bring up the Claude example again. where the weights are selectively modified to drive the system to some particular state. So in this blog post from Antharpy, for example, they demonstrate how they made their LLM plot, just really eager to talk about the golden gate bridge by a similar this talk is geared around sparking more biologically inspired ideas like this. And so Gita asked us to do a tutorial overview about neuromodulatory methods in the brain and how they might apply to large language models. So to do this, I'll first present a high-level overview of our knowledge of neuromodulation systems with a focus on mammalian neurobiology. So I won't be going into detailed mechanisms. I'll instead keep the focus on their hypothesized roles in cognition. And so our goal is to touch on biological solutions that may be relevant for the ongoing projects in the language of that topic area. And I want to stress that these are hypotheses, still up for debate, but might be worth exploring and evaluating. Mark will then present recent work that leverages these mechanisms in the machine learning literature with a focus on the field of tiny like one learning. Finally, we'll close out the talk with some consideration for ideas on light questions. All right, so jumping right in. So there are 4 major neuromodulatory systems in the mammalian brain. These are the cholinergic, dopaminergic, noradrenergic, serotonergic, and neuromodulatory systems. Try saying that 5 times fast. I'll start off by considering how kind of a simple case. So a neuromodulatory system that helps animals make decisions on a moment-to-moment basis. The serotonergic system has been implicated in a wide range of decision-making functions. Serotonin is produced by the raphe nuclei at the brainstem and reaches most 4 brain areas, including the cortex, ventral striatum, hippocampus, and amygdala. So serotonin has been implicated in mediating the trade-off between decisions that result in short-term rewards and that which would result in a future potentially life-term reward. Specifically, high serotonergic neuron activity results in a more likely outcome to wait longer for a delayed reward, and depletion of serotonin in the forebrain leads to impulsive actions. Yes.
Sorry, can you go back?
Yes.
That's, I guess these things go everywhere. But does that particularly get osteometry or single?
I think that might be more implicated in ACC. I didn't see the ACC specific sorry. So similar effects have been observed in humans. So what they do is they force humans to go on this diet. They'll deficit just like low levels of tryptophan, so you don't have as much serotonin in your brain, and then they watch what the behavior is. And so we see similar effects of impulsivity with serotonin deficits in humans. And so these observations have led to a natural interpretation within reinforcement learning, a machine learning paradigm in which an agent learns how to interact with its environment in such a way to maximize the average rewards it receives. And so this equation on the right describes how temporal difference error, delta, relates to the word provided, R, as well as a weighted difference in value estimates at different time points. And so in a 2002 paper, Kenji Doya related serotonin to the temporal discounting factor gamma, which has since been confirmed in follow-up studies. And so building on the reinforcement learning model, serotonin has also been linked to the prediction of punishment to support avoidance of behavior resulting in harm. Fools and colleagues in 2008 showed that the same dietary intervention also saw human subjects make more errors for harmful than rewarding stimuli in a reversal learning task. And this led to multiple models of serotonin as also appraising the cost of an action within the reinforcement learning framework. So the findings I just reviewed seem to indicate that we have a way to predict punishment in the environment, but what about reward? So for that, we can turn our attention to the dopaminergic system, which you're probably most familiar with. So dopamine originates in the ventral tegmental area as well as the substantia nigra of the mammalian brain. The VTA targets the cortex and the nucleus accumbens of the basal ganglia, while the SNC targets the striatum. And so dopamine has been implicated in reinforcement learning as well, due to recordings from dopamine neurons during the conditioning task. And so on the left here, I have an example of an unpredicted award. So there was no prior conditioning associated with it. And so in this case, when a drop of rewarding liquid occurs unexpectedly, dopamine neurons are activated because the occurrence of the reward was a positive prediction. In contrast, when that reward starts to be associated with a conditioned stimulus, when the reward is presented, there's no response from these neurons. There's still a prediction. There's still a response at the conditioning presentation. And then finally, when a reward is predicted but not presented, these neurons have reduced their activity, indicating a failure of the model. Okay, so this view of dopamine in signaling unexpected rewarding stimuli has been really easy to grasp in popular science. But are these memes I found on the internet entirely accurate? And of course, the answer is not entirely.
What's the small text on the bottom right?
This? Yeah.
Yeah, read us our memes.
Oh. Why is no one having a good time? I specifically requested this. So there are several lines of evidence that undermine this interpretation of dopamine's role. First, dopamine neurons, recordings from dopamine neurons reveal that they seem to respond to any salient or novel input from the environment, regardless of its reward value. A second challenge comes from the fact that they respond too quickly to reward predicting stimuli to have been generated by the most plausible source, which is the cortex. And last but not least, dopamine's depletion does not actually affect learning, which that reinforces model fish.
The first point is there's still an effect of like a stimulus that's been shown a lot of times kind of saturated, or we continue to respond to the same stimulus without switching newness. You know what I mean?
Yeah. I think I can't remember exactly. I think there is some staining if it's not also reporting. I'm not quite sure. Yeah, sorry. So these challenges have elicited numerous proposals from the community in what has become known as the saliency hypothesis. Redgrave and Gurney proposed that dopamine has fired in response to novel environmental events to support discovery of novel actions. And so this is distinct from the prediction error hypothesis, where reward prediction errors are used to update the meaning of a set of defined actions. And Carl Friston moved to a different modeling framework entirely, that of Bayesian inference, that to formalize what is called the uncertainty hypothesis, not to be confused with the uncertainty principle in quantum mechanics. Specifically, he proposed that dopamine encodes the precision of beliefs about alternative actions. And so in this way, misrepresentation of precision would result in inappropriate incorporation of new information with prior beliefs. And so what's interesting is that in both of these views, dopamine can be seen as kind of regulating the information that can influence behavioral decisions. And so let's take stock of what we have so far. In this way, serotonergic and dopaminergic systems are kind of often in a dependency relationship. So in a neuromorphic example of a robotic model of serotonin, dopamine dependency, the robot exhibited kind of withdrawn safety-seeking behavior when serotonin levels were high. So it like walk along the wall, kind of gets covered. This is called pigmotaxis in the behavioral neuroscience literature, where it would go directly to its charge port. And when dopamine neurons were high, it would seek out risk-seeking behavior, such as moving to the center of the brain or investigating a novel object. I know Michael had a robot that became a neurocyst too. He made it afraid of its own agents on something. Yeah.
What makes the center of the drum scary? This substance.
I'm not quite sure how the authors mediated that, but within the, I guess, within the ecology literature, it doesn't provide as much cover as the side of the walls would. Or just very exposed. And then yeah, in like for nocturnal animals such as mice, really high light levels are also making more susceptible to predation. I'm not quite sure how they built that in. So far we have discussed two neuromodulatory systems and their effect on producing purposeful behaviors. However, we also saw that dopamine may play a key role in information gaining to support building a useful, that is advantageous to survival, internal model of the world. And so this idea of an internal model of the world allows an agent to make predictions about what it can expect to observe. And so when are these expectations violated, the noradrenergic system comes online. So noradrenergic neurons are located in the locus coeruleus, which receive input from the brainstem, amygdala, and prefrontal cortex, which positions it to integrate information about autonomic, emotional, as well as cognitive functions. This signal is then broadcasted to nearly every region of the brain, except the basal ganglia, surprisingly. So what happens to the brain when such an event occurs? So phasic activation of the LC has been associated with shifting attention from an expected stimulus, such as that related to performing a task, to an unexpected or novel stimulus, such as distraction from that task shown here on the right. And when I first saw this, I thought that was Post Malone. And I was like, it was very unexpected to see in a paper, but it wasn't. I zoomed in. So these attention states are in turn associated with different patterns of brain-wide activity, shown in blue, which is the dorsal attention network, and in orange, which is the ventral attention network. Having one's expectations violated is a signal that one's internal beliefs need to be changed. And interestingly, numerous studies have linked pupillary responses, which are strongly correlated with LC activity, with the learning rate in a Bayesian belief model. And so because of this two-step correlation between pupillary responses and LC activity and pupillary responses and update rate, LC activity has been proposed as a proxy for the learning rate in those Bayesian update models. So then noradrenergic system plays a role in shifting attention, but what happens once we've effectively oriented to that new state? So this brings us to kind of a third and final theme of neuromodulatory effects of attending to sensory input, for which the cholinergic system has been the most extensively implicated. So the major sources of acetylcholine are located in the basal forebrain and the brainstem. Today I'm going to focus on those from the basal forebrain, which include the medial septum, the vertebral limb of the diagonal bend of the Broca, VDB, and the nucleus basalis of Maynard. So cholinergic neurons in turn target many regions of the brain, including those serving sensory processing, executive function, and emotional roles. Substantia nominata originating ACH projections target the prefrontal and parietal cortices to increase attention to salient objects. So attention is strongly mediated by ACH during projection to sensory cortices, and cholinergic inputs to visual cortex can enhance the gain of those sensory inputs and play an important role in detecting cues. Interestingly, the cholinergic system plays a major role in memory consolidation through its targets in the hippocampus, Specifically, when ACH activity is low, memory retrieval is enhanced by strengthening recurrent activity relative to cortical input, while high ACH enhances sensory input, allowing memory to be encoded. So intriguingly, these patterns are observed in a slow wave and wake or REM sleep, respectively. So there might be some ideas for the Tree of Dreams project here. And so the ability to regulate the relative weighting of new information from the environment with that stored in recurrent connections is useful for rationally updating one's internal beliefs about the world. You and Dan put forward a Bayesian statistical theory that suggests that acetylcholine and noradrenaline encode expected and unexpected uncertainty, respectively. So these neurotransmitter systems adjust perceptual inference by balancing sensory information with prior knowledge, thereby influencing learning. So within a Bayesian framework, the posterior distribution perception is shaped by the likelihood sensory inputs and prior distributions are top-down expectations. So in this context, the probability of hypothesis given the data represents the posterior distribution. The PDH is the likelihood function, analogous to the sensory inputs, and P of H is the prior. Z is a normalized factor. And so uncertainty is crucial in this model, as it determines the relative importance of priors versus sensory inputs when making inferences. And so this makes sense, right? When prior uncertainty is high, optimal inference suggests that sensory inputs should be given more weight, and learning should be enhanced to update those priors. And so on. Yep.
Talk a little bit about the timescales of which we're describing these effects.
I don't know. Sorry. Yeah.
I'm wondering if it's like I'm in an uncertain mood, or it's like for a specific calculation, I am feeling about the quality of my efforts.
Yeah. Yeah, that's a really good question. Yeah, I didn't look into that.
Works.
No. So I'll hand things over to Marco now, but let's pop Grace if you've been paying attention. Another big for you to have an idea. Any thoughts on what neuromodulatory deficit this person might be suffering from?
That's impulsive.
That's right. Serotonin.
Yeah, sorry.
That we have to spell out the modulation works in the biology. So now I need to try to describe how this idea of neuromodulation has been adopted into for elements in general. So, spoiler alert, neuromodulation has been mostly applied for neuromodulation of synaptic plasticity, not many other applications actually. So, I'm going to sketch just a few words. But first, I would like to focus on this idea of the three-factor learning rules. So maybe we are very familiar with the concept of Hebbian learning rules, where we have like this phrase of far together, wide together, like we have inputs, outputs, and if both there is a correlation, we change the synaptic connections. But there's also this idea of three-factor learning rules that we don't only have we have inputs, we have outputs, but also we have some learning signals that change from a more global system. So for example, in this particular diagram, we have 3 neurons, we have some input spikes, and all this neuron is going to fire. So we have the presynaptic activity and postsynaptic activity. The correlation between these inputs and outputs is going to produce a synaptic flag called eligibility trace. So that means that when the target signal came from that target signal, meaning neuromodulatory chemistry signal came into the picture, this synaptic connection is going to be updated. So even when we have some inputs here, or we have some outputs here in these other connections, all those other synaptic connections, we don't change any of the weights. So essentially what happened in this idea of three-factor learning rules, we have the modulatory signal, a function of the inputs and function of the outputs. So the synaptic connections are going to be updated as the product of this global learning signal and the eligibility trace that is basically a low-pass filter of the combination of inputs and outputs. So we could argue in some way that BPGT back regression through time is a kind of three-factor learning signal. If we write the equations and we apply some change of variables, we can see that for a spiking neural network in this particular example, and running time, we can obtain a learning signal, a function of the outputs, and a low-pass filter of the input. The problem here is that the learning signal depends on the future time steps. So it's not local time. And also PPTT has this complexity of Tn, meaning that T the number of time steps of the task and N the number of neurons. So it's going to scale if we increase that sequence. Now, based on this idea of the eligibility traces in 2020, some researchers proposed EPROB. EPROB is that take advantage of this particular idea to develop a local learning rule that can capture the dynamics of the spiking activity without the constraint of the time. So the memory complexity of this particular learning rule is going to be independent of time. So here we have the eligibility traces as in the first definition, like a low-pass filter of the inputs and outputs, plus some local learning signal. This local learning signal is going to be generated by some random feedback connections, or could be generated by observation through the layers, but it could be at any of those points. So what they have some very nice experiments. So for example, in this very simple experiment is you have a layer that is going to receive some cues on the right side or left side, and the task is the agent has to decide in which of the sides, right of left, the agent receive more inputs. So we have the signals left, right, and then we have some delay of couple of between half a second and 1 second. And then we have a learning signal that comes into the picture to force the agent to decide what is the in which side he received more input. So we have here the spiking activities, the neurons are going to fire, and this spiking is going to produce the production of this eligibility trace signal. So as you can see, depending on the activity, if there is firing inputs and outputs, then we are going to produce a signal that is going to decay exponentially over time, but can capture temporal dynamics over several seconds. So essentially, if you compare this small spiking neural network with backpropagation, EPROB can produce the same kind of performance, the same kind of decision error, but being temporarily local. And it's very nice because this kind of learning rules are more friendly to be implemented on hardware. So there's a chip that was proposed in 2022, is the Recon. So they using a C5 version of this EPROB learning rule for spiking neural networks. So here the diagram is quite simple actually. So we have here the forward weights, the recurrent connections, and we have the logic for the eligibility traces. So essentially we can implement with that, we can take this learning signal, temporal local learning signal for some on-chip learning task. What we test this researchers find is that for event-based data sets specifically, this kind of learning architecture is more energy efficient. So what I was trying to say is that we can take advantage of these kind of ideas to make more efficient hardware as well. So also neuromodulation has been applied for ANNs. There's a nice work called backdopamine. They try to design this kind of learning rule inspired by the dopamine effects on plasticity. And essentially, it's a kind of a meta-learning approach. So they have the weights, the fixed weights, and they have some plastic weights. So essentially, they have those weights are just the formal weights that we all know, or the current weights. But additionally, they have some dynamics. So it's like more or less how our brain works in some way, right? Because we don't have fixed weights. Our weights are always changing. So they try to modulate that kind of effect. So they propose two simple neuromodulation approaches for these plastic weights. One could be just simply taking the error or reward signal and modulating the Hebbian plasticity, or taking the eliminated traces that we discussed before and take this error signal to modulate that kind of eliminated traces. Sorry. So what they found is that actually this kind of rewrite modulation or simple modulation can help the model to obtain a better performance on then relative complex tasks than to write some sequential learning. So, for example, here we have the engineer that is going to receive some kilos, and it's going to have to decide between if maybe it has seen some particular cues or not, or it has to solve a navigation task. Find, for example, this in general is the engine, and we have the reward signal in V. So the engine has to move in the maze to find this particular reward signal. So if we don't do any plasticity, or we don't modulate the plastic connections, we can see that we cannot solve this kind of task. Like the performance is really bad. But if we introduce this idea of neuromodulation and modulate these heavy learning rules or LEP traces, then the performance boosts significantly. So, that is essentially what I wanted to share. As I was mentioning, this idea of neuromodulation has been mostly applied for, how we can modulate that synaptic plasticity just for local learning rules to obtain the improvements in memory or computational over number of operations, or to obtain better performance over sequential tasks. Thank you.
I wonder the concept of stops the sequential tasks. How is it implemented that you're doing something, you're doing it well, and then you enforce it to go the same way, or how? Or just as a mechanism? It was just demonstrated as a mechanism, or was it also done in form of the task where it makes sense semantically? For example, if I'm doing something well, then I'm changing my decision making as an involved. So, or if I find the correct then those work, then I'm going with more straight than somehow. So I wonder, was it done in any task, or it was just demonstrated that the mechanism works?
I'm not completely sure. So essentially what this kind of approaches has been doing is we can take this idea of neuromodulation and try to do some meta learning, like learning to the because at the end, this neuromodulation is going to play the role of a learning rate kind of signal, and it's going to allow the model to encode temporal information in memory in this way. But decision that's what it's kind of that's something.
Cornelia would you be skeptical that of learning in that context?
No.
Do you think it would work?
No, I mean, I see that this is a good mechanism to modulate the needs. Great. I wonder whether there's been an application where this makes sense in a continuous way. It would make sense, right? That's doing something well, giving enforcing this, not serotonin, but dopamine. Keep going that way. Gives me expectations, what I should force. Because you said, learning. Yeah.
Maybe add the questions that, because I think that's
my knowledge, right? I think all these things are beautiful in principle, but as soon as you localize things, right, you're going to create some bounds. Like you're not going to approximate the errors exactly, right? But I think it's my knowledge that I think some of the continual tasks run into problems because if you don't get a good optimization out of your locality, then it crashes. Right?
Okay, yeah, actually, sorry, maybe I misspoken, but this particular local learning model, what they are trying to do is encode these temporal dynamics into a local temporal variable called a trace. But the learning signal itself can come from a different module. So it's not bounded by by the locality itself. Like you can have a learning signal that is like updated very you can update from that location perfectly learning signal. But just to keep the temporal locality, you can reduce out.
Yeah, okay, because I mean, okay, so I recall the paper going through some years ago, but I recall that specifically this learning signal what we look like we kind of fit through the network, right? Meaning you would approximate it over time. You wouldn't have a global signal like a backwards somebody freeze everything as I hear the error. Like you have to propagate it over time, right? Which means it will not be perfect, right?
It would not be perfect if we are talking about that task that you know that you feature back steps. But if you are learning online, then it's going to be perfect because you don't have information from the future time steps. So essentially, what this variable called LDT traces is trying to just encode all the temporal information, so you don't have to store every single state in the memory.
I'm not sure I understood that, but I can ask you afterwards.
Shake.
So he has his better, right? That's
Nice presentation. Cool. Like in street vector learning, for me, I'm always a little bit concerned. So just because you have this heavy eligibility trace, which would say like, yeah, these neurons had correlated firings in these circumstances, it can be that their contribution to the overall output is inverted given the global output, right? Like it could be that it was an erroneous, like that the activity of any particular neurons, while correlated given that trial, might actually be contributing negatively towards the reward signal. Like most of them would be correct, but then there's probably some outliers that were actually not good to reinforce. I'm just wondering if maybe through comparing with backcrop, although I don't know how much sense that makes the time, if you could take some statistics on how often you're making the perfect update given an eligibility trace and a reward signal versus the amount of times it's maybe right.
Yeah, so essentially, there are two parts, right? Here we have the main signal is the neuromodulation that we are talking about, and then we have the eligibility trace. So this eligibility trace encode the temporally all the history of the network into one particular variable. So the performance is not only going to be treated by this learning signal, not the eligibility trace itself. So for this work, they proposed like multiple ways to produce that learning signal, like using some random pivot connections. And of course, random pivot connections are not as good as having some propagation to the layers. But you can generate the learning signal also by using backpropagation, and that is going to give you good performance. So for example, it's just this particular learning rule has this kind of memory complexity O in the square, and it's not very friendly when you scale for very deep neural networks. So there are a lot of works that try to make this complexity more linear by changing the eligibility traces. So for example, I have been working on a kind of eligibility trace that take the STDP kind of dynamics to make this memory complexity linear and taking the learning signal as some propagation through the layers. So you can have temporal locality, but low memory complexity. And you can match the performance of PPDD for sequential tasks, or even go a little beyond.
I see. So in your case, the eligibility trace is the local part. And then the third factor, you actually are tracing backwards.
Yeah, so nice. So
So it is.
third factor and anyways,
In the machine learning aspect, the neuromodulation is directly in the semantic rate updates. If the biological portion of the topic wasn't clear, that was always the case, or necessarily the case. What do you think of that?
It's biologically inspired, not biologically plausible.
I guess maybe do you think there's something about having semantic learning is an important part of data. And also, some of the cleverest and most humble neuromarkers do a lot of work in the activities of the semantic ways. So do you think that neuromodulation could be affecting those kinds of computations? Learning just remove exclusively the semantic way, and maybe that would help the artificial data.
National development.
so do you mean modulating the activity itself? So actually, we actually reading like these pieces, I can use some kind of transformers in a specific gating system. So the secondary network is going to place this neurons on this modulation by gating the activities. So it's some kind of looking into that, and they achieve like small improvement in question answering and that's. So this actually you can.
Yeah, like the question of, are there other aspects of the aspects of neuromodulation that aren't just directly classically related, whether that it's just experimentation? It's kind of more at that level. When I observed that the my plasticity wasn't working on the thing towards neuromodulations that you
Cholinergic.
the cholinergic one, which said at this balance between recall and attending to exacerbate, which kind of imagine being useful, biology for moments when the things that happen right now are what versus the things where it's not really interested in my experience. It's don't really care what's happening. Well, it's just people attend talks where that figure out by there. One observation that I would make is that this does come up quite a lot in the form of the structure that people build around LLMs these days. And so there's kind of this observation that you're relying on long-term memories, your transformer architecture. So that's your 100 billion parameters of a transformer, right? And that's kind of like the stored knowledge. And you might ask a question, the stored knowledge is not sufficient. And so there is really oftentimes really poor calibration. So you get it to admit that it doesn't know something versus try to hallucinate something fact of the short knowledge. That's possible. And then what people have done is started to kind of build structure around that says, well, if you don't have good stored knowledge, then we should be looking to an external memory store, like a database, with the facts that are relevant. You directly retrieve those and shove them into the context of that query that's typed. Now it might say, what's the like nitrogen, and then you have a bunch of facts about nitrogen that just got shoved in, explicitly retrieved. And so deciding when you do one versus when you do the other, it's very problem. And it's an area where you could, there might be some lessons learned from biology, both in terms of what does it mean to be uncertain? How do you decide how does the brain decide when it's uncertain, and therefore kind of contributing that effect?
Like along the edge of the seat. How does the brain know when it's uncertain?
With me, check.
How does the brain know when it's uncertain?
One of the things we've been doing is our representation probabilities with things, all algebras. One of the things we've also found is that by modulating the neural representation. If we start modulating the lake representation by extension neural representation, we can change the certainty or basically the peakiness or the width of the distribution. And long story for how that be a curate.
When you say modulating the representation, what does that mean? It's just
In this case, it actually means like trying neurons, which you could imagine be different, probably fiction or some other aspect. And then also you've probably done some stuff on this too, right? About how we make case.
Stick a thing.
The things you could and ultimately watch it. Well, like neurons. Well, that's pretty good. Your brain's only sort of wet. You know, she's like pretty deep and it's not sensory, but
Would it be possible to like, would it be worth trying to sleep something down or resident just idea like if your prediction is uncertain to some extent, just face them out and try to
certain word ways.
basically like something.
so turn it over to Valentine green time.
Thank you again. This is awesome.
Really appreciate you pointing.
Okay, so I'm really, really pleased to have Steve Zucker here, and he came a little late, so he missed a few of the lectures. But he's been coming to this meeting now for 20 years, I think.
I'm not that old. We no longer do that calculation in my family.
Okay, let's not go there. Okay, no, but what his background is in computer vision, and he has written some of the most influential articles and things that now are standard in computer vision. Before any of the recent explosion that's occurred with convolutional neural networks and so forth. And the reason is that vision is a very deep subject. That's to say, it's not just a lot of neural networks, a lot of training, which a lot of people think it is today, but there's a very, very deep knowledge that we have from studying behavior, psychophysics. Psychophysics means you do visual experiments. And I gave you an example of one, the Kinesis triangle, right?
Right.
So we wanted to be able to understand that. So it's really important that you understand the psychophysics, the behavior, how human visual system is actually works, and not just from the perspective of behavior, but also from the properties of neurons in the visual cortex. And that's going to be the theme of Steve's talk. He's at Yale University. Before that, he was at McGill. And before that, he was at the University of Maryland. So that's where he's from.
Thanks, Terry. It's always a delight to be here. And I just wonder, I brought your hat back.
That's mine, actually.
It's not mine. And in conclusion, let me say that the shape of the hat is very much like the Laplacian of the Gaussian. So I'm going to talk about ways of thinking and inferring organizations of neurons in the visual system of the mouse. And it will tie in a lot to several of the talks I heard over the past few days. In some sense, it's a formal inverse to Mackenzie's talk. In some sense, it's a way of thinking about population activity in a modern way. And in some ways, it's a way for people in this crowd who I learned over the last couple of days are very oriented toward modern machine learning, AI techniques, and things like deep networks and whatnot. And as everyone in this room knows, these deep networks are crushing ImageNet, are doing really well at matching that stuff. As everyone in this room knows, deep convolutional networks had their origin in a cartoon model that Hubel and Wiesel set up in the late 1960s for the visual system in the cat.
By the way, Steve, those two figures were not in biological cybernetics. They were in the 1968 Journal of Physiology paper that Hugo Wiesel actually published with the first recordings from single neurons in the visual cortex. And they discovered simple cells, which is on the left.
Yeah.
You see that's a cortical cell that's getting input from the LGN. And then what you see on the right is a complex cell, which is getting input from a lot of simple cells. That's a neural network model. They had a neural network model in their very first pioneering paper.
Yep. I apologize for pasting this thing up there rather than down here. But the Fukushima model was the first model to do MNIST. And it occurred some time ago. And it is the basis for much of the thinking about modern networks. I don't care about that. I've had the luxury of moving in my career from having to work on technology applications and making that money required to send my children through school to being able to pursue science. This leads me to think of another view of these, which is this Manhattan Project that you also mentioned by Jim DiCarlo, Dan Yeamans, all these guys. There's this Manhattan Project that asserts that these AI networks are a model for the visual systems in the brain. And they are currently thought to be the best model. They explain by various measures that these people create, they explain a remarkable 65% or so of the variance in the neural recordings. Are they the right model to be using? Are deep networks really a model for the visual system in the primate brain?
Well, let's take a vote. How many agree that, that this?
Guys, stay down, shut up.
You brought this up. I suspect you'd be surprised by the answers. Again, how many people think that convolutional networks are a good model for the hierarchy of the visual cortex? Put your hand up.
It's a decent first model, yeah, definitely.
Okay. There's two hands up. It means that the rest aren't convinced.
How many think they're not? How many think they're not?
I mean, they're not a complete model, obviously, but they're still a useful model.
Question, are they better than nothing?
Okay, better than nothing. Okay.
Are they better than nothing? That's a really good way to pose it. Yeah.
But wait a second now. Models, all models are wrong, but some are more useful than others, right?
Right.
But this is the wrong architecture.
Right.
Okay, well now we'll hear.
So how might we answer this question? Well, that's really what this talk is about. And so there's two ways to read this. One is, am I really interested in establishing a formal mechanism to say whether deep networks are models for brains? Or am I really interested in figuring out how brains might be wired up? And that's the question. And the first step to do that is to figure out what neurons are doing and which neurons are like each other, et cetera. That's what this talk is about. So how do you do this? You have some unknown neural network. You probe it with some stimulus. You get some spikes. You get a bunch of data, neurons by spikes. You do some data analysis. What do? Well, there have been people who've worked on this. One of the first questions is, if your goal is to understand the functional organization, and tonight I'll be talking about the mouse, but this talk needn't be limited to that. If your goal is to understand the functional organization of the mouse, what is the right way of thinking about networks? What's the right way of thinking about visual stimulus? What's the right kind of analysis to be doing? And let me start with something to set you up to think about the mouse. So many people think the mouse is really a terrible model for studying vision. And there's a quote from Tony Movshin, which informally can be referred to as "Why study vision in an animal that's blind?" Now, why would Tony say that? Well, Michael Stryker
catch a mouse in the field.
Sorry, no. So Michael Stryker and Chris Neal were the first to show that these simple cells that were 2 slides back from Hugel, Wiesel, and Cat exist in the visual cortex of the mouse, and they characterized them using spatial frequency gratings. And they found this distribution of cells that care about different frequencies of those gratings. And you can see the peak here is at 0.04 cycles per degree. So what's 0.04 cycles per degree? 1 degree is you hold your arm out straight, you look dead on at your thumbnail. That's about a degree of visual angle, right? So we want 0.04 parts of a sinusoid to fit through that, right? So the receptor fields in the mouse measured with spatial frequency gratings suggest that the mouse is looking through these Coke bottle eyeballs and is seeing this incredibly blurry version.
They would never pass a DMV test.
They could not get a driver's license. That is correct. Because they would, from the perspective of the Department of Motor Vehicles, they would be viewed as blind, right? So here's the same image as seen at the resolution of a primate, as seen at the resolution of a mouse, filtered at this frequency. And you can see there's not much there. Now, there's tons going on behind this. One of which is, the logic is that receptor fields are filters. These filters are what define what goes on in the early visual system. They're like the filters in convolutional neural networks, about which we've heard quite a bit. The visual structure is lost to blur because these filters are tuned to such low frequencies, and the mice are blind. But as Michael points out, they're really good at capturing crickets in the wild. They're really a great system to use because of all the genetic and imaging machinery that Mackenzie talked about last night and this morning.
John, raptors think we're blind.
Yeah.
Yeah.
Right, there we go.
Yeah.
We can't study vision in raptors because humans are blind. So everybody's blind for somebody else, right?
This has been challenged, right? Like there's been more analysis.
Oh, you're gonna hear this.
Yeah, okay.
So maybe the problem here is spatial frequency gratings are a poor quality stimulus.
Exactly.
Keep that in mind.
Totally.
Yeah. So if that's the case, what is the right way to think about a mouse? So we at Yale went into our mouse, we put on our mouse hats. We said, what should we do today? We said, let's run around through fields. So when you run around through a field, what do you see? Well, there's all this grass and junk flowing by as you're running through the field. So you see this kind of flow with oriented structure passing by you, kind of this waterfall of structure. And so maybe if that's the world the mouse lives in, maybe we should use stimuli that are more ecologically appropriate for the mouse, like, say, a mathematician's approximation to what these flows might look like. And so we have various versions of these, different signs of contrast, different amounts of orientation, so on and so forth. And here's a version of some of them. We do single dots, we do triples of dots. They flow along. It's a pretty interesting stimulus. They're not completely rigid, so the mouse sees a little bit of structure, so on and so forth. But the key idea is to think of these flows as a class of stimuli that are more interesting to the mouse, possibly, than spatial frequency gratings, but maybe more easy to analyze than so-called natural scenes. Now, Mackenzie commented today that the space of natural scenes is arbitrarily large. The more scenes you have, the more dimensions that arise. And the Rockefeller group has claimed that the dimension of this grows without bound in the number of scenes. I don't know if that's true. Is there any way to actually analyze information from natural scenes? Put that on the side burner till the talk is 3/4 of the way through.
Also, are those mice mostly nocturnal or diurnal? Are they daytime or nighttime? It's wild mice. I don't know when they.
Yeah, so these are not natural mice. These are UCSF laboratory mice, and they live during the day, they sleep at night, and if Michael were here, he would tell you a lot about them.
No,
But-
but they're on an inverted light cycle.
Yeah,
They're still most active diurnally.
Yeah, so there's a part to this that's extremely relevant to things that came up in your talk and others, which is Stryker and Chris Neal showed that the visual responses in mouse cortex are a function of whether the mouse is running or not. And so we took great pains to make sure they were not running in all the stimuli that I'll show you. So we factored out the motion component for this lecture. Okay, so the claim is that these flows are an interesting class of stimuli. And so how do we get data for this? Well, this is Michael's lab, and it's set up so the mouse has a bar cemented to his skull, which is fixed, and there's a hole in the skull. That third beer was a bad idea. There's a hole in the skull, and there's a multi-electrode passing through. But the mouse doesn't really know that he's in this fixed arrangement because he's standing on a trackball, which is sitting on a jet of air, and this is a structure that David Tank developed, modeled after Werner Reichardt's fly setup. So the ball has the same moment of inertia as the mouse. So the mouse is looking at computer screens, and he's running around on this ball, and he doesn't know he's not going anywhere because the world is changing, and he's running around, and everything feels cool. Okay, so we show him these various patterns. We get data. What do we see? Okay, so here's an actual receptor field from Michael and Chris. And you can see it's got an excitatory center, inhibitory surround. You get these beautiful simple cell-like receptive fields. Here's a this is a Gabor filter model of a receptive field at 0.04 cycles per degree, the so-called optimal spatial frequency. You could say for our low frequency flow patterns, there's a bunch of elements in the excitatory portion, the inhibitory portion. You do the convolution, and Toby will say it goes to zero, right? You go to the higher frequency flows, there's a zillion components in each zone, integrates to zero. You shouldn't see anything, right? But in fact, the visual system in the mouse is really excited beautifully by these stimuli. Most neurons don't like only these gratings. Most neurons like all the stimuli. They don't care. They like gratings, flows. They're in some big complicated network. They're doing something that we don't really understand. So this makes our little diagram a bit trickier, right? Because now we have a whole bunch of stimuli, gratings, flows, blah, blah, blah. We have a whole bunch of stimuli. We feed those into the network. We get a bunch of data. And the data are typically viewed as a big matrix of neurons by spikes in time. So this is a data matrix. And then there's various ways to build these. You can put the different stimuli together. How do you analyze this stuff? Well, we're clearly not the first group of people to worry about this. And what most people do is they say, well, the trials with stimulus A, trials with stimulus B, trials with stimulus C, that's what I really care about. So let me build the kind of manifold that Mackenzie was talking about this morning, which is widely used in visual perception. Oh, that's an allergy, Toby. Excuse me. And so how should you read this manifold, right? So you could, for example, you have a data matrix here, you could PCA it, but let me walk you through the way to think about the PCA. We have neuron 1, we show it, we have stimulus 1, we have recordings from neuron 1, neuron 2, ... neuron 1000. So you see this 1,000 dimensional space, okay? Show stimulus 1, It's a point in that space because neuron 1 responds to some extent, neuron 2 responds to some extent, etc. Right? Show stimulus 2 might be from the same class, might be from a different class. It's another point in that space. And typically what people care about is whether this manifold in neural coordinate space is a clustered manifold. And that's really important if you want to read out what the animal was looking at. So in the literature, this is called the state of the brain. And to build a brain to computer interface to infer what the animal was looking at, you want to have a map from some point in this space to a stimulus. Well, it's easy. It's really easy, okay? However, this is why we call this a decoding manifold, because it's really useful for decoding what the animal was looking at. That's the word you used in your talk. And the key point is each point is a trial. Now, if our business is not to build brain-machine interfaces, but to figure out what's going on in the mouse's brain, we don't want that manifold. We want a different manifold. We want a manifold on which each point is a neuron, and the manifold is embedded in a space which involves the outer product of all the stimuli and the responses of the neurons with respect to that. We want a manifold in which each point is a neuron. So now think about it from a geometric perspective. Over here, each point on the manifold is a trial. So if I walk on the manifold, I'm walking from trial to trial. I don't actually, I'm looking at how the state of the brain changes. I don't know anything about how individual neurons are changing, right? Over here, if I walk along the manifold, I'm walking from neuron to neuron. I could ask, what is it about the stimulus or the response that's different? And those are the directions that indicate the first view of circuitry. Yeah.
Is this like the trajectory of the manifold in the first case?
Trajectory. Yeah, you mean if we walked across? Yeah, that would be a trajectory. Yeah. And I'm going to talk about those trajectories in a little bit. I'm going to illuminate a few of them for you. Okay. So we call our manifold a neural encoding manifold. Remember, each point on the manifold is a neuron, and nearby neurons on the manifold respond similarly in time. Their spikes are similar to similar stimuli from this ensemble of stimuli. Okay, so you see the game. And once we have this manifold, if we look at cross coordinates on it, that could tell us something about who's connected to whom and why. Yeah.
So this is not rate coding.
This is not rate coding. No. I'm going to show you in more detail what the representation of what I call respond similarly is, and we turn that into a rate function just because it makes the analysis easier. But we're not looking only at rate coding. Okay. Yeah.
Are you going to get into how you built this? Is it also?
Yeah, that's where I'm going.
Okay.
Yeah, that's where I'm going.
And is it effectively, and maybe in some settings, recovering like the topographic organization of?
No, it's a functional organization, not topography.
Okay.
It's often the case that nearby neurons in function are topographically nearby each other, but this is not that. This is a very abstract manifold based on functional properties. There's a lot to be said for that, though, and I could. Okay. So first thing to note is, because the responses to our ensemble of stimuli with the flows and things were so much more vigorous than Michael and Chris expected, we thought, well, we better know what the input is to the cortex. And so we expanded our group to include Greg Field, who is a great retinal physiologist who was at Duke and now is at UCLA. Okay. And there's slightly different aspects of how we do the recordings. These are done by excising the retina and placing it on an array These are done by inserting a multi-electrode directly into the brain. I know you're thinking, what about eye movements, right? Because there's eye movements here, they're right over there. We record the eye movements here and play them back over here. So we have a lot of controls that are in place. Let me tell you about the stimulus ensemble, low frequency, high frequency gratings. Everybody uses those, you have to, plus our flows. And we separate the flows into those that just have a motion component, a directionality component, and those that have some orientation associated with it for obvious reasons in thinking about V1, okay? Here is the kind of data that we would get from those trials. If we build the perceptual manifold, like using, this is a simpler algorithm than Mackenzie's, but her algorithm would yield something very similar to this, I'm pretty sure. Then in PC coordinates, that is in linear functions over the ensemble of neurons, the trials form these beautiful clusters, right? So you're saying, oh, great, mouse cortex, stick this striker multi-electrode in there. We can tell you what the mouse was looking at. We can read his mind. Okay. Do the same thing in the retina. Whoa, this is weird, right? The retina has even bigger margins between the categories than the cortex. So if we're going to do this, if I were Carver Mead, I'd say, let's do this in the retina. It's stupid to do in the cortex. This is a harder classifier to build than this, okay? It's even more complicated. The retina is a much lower dimensional clustered manifold than the cortex. What is going on here? What is going on here?
So what layer is this section V1?
It's across layers.
Oh, it's across
It's
layers.
across layers.
Okay.
And I took most of the layer stuff out of this talk.
Yeah,
because-
sure, no problem.
Yeah,
No, that's great.
but it's across layers.
Great.
So let me get you used to looking at how I'm going to display the data to you, because you'll need this. Okay. So we have a retina, we're recording from a retinal ganglion cell, and the stimulus is drifting in this direction, and we do multiple trials. And you can see that, boom, there's a bunch of activity, it's quiet, there's a bunch of activity, it's quiet. When the stimulus drifts that way, when it drifts up, there's similar sort of thing. So we can take this continuous function here and display it as an image along this line. You see that? Now we take this one here, we display what direction? That's up, so that's this line here, right? Now, how should you be thinking about that? Does this representation make sense? Well, you know what a retinal ganglion cell receptor field looks like. It's got, I show an example here with an on center and off surround. So you have this Mexican, where'd the hat go? Right? We have this Mexican hat over here. We have this grating drifting by, it goes. So you see that, right? And that's this, right? You see that perfectly, right? What's V1? V1 receptive field, they're oriented, blah, 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 right? So these guys are going to be orientationally selective. For a cell whose receptive field is at this orientation, they're going to like patterns that are drifting across like this. So that's a Hubel-Wiesel simple cell, and there it is. Right, you see it drifting across, and it only likes the stuff that's going this way and this way. It doesn't like the stuff going this way, right? So that's how to read that. So we call these PSTHs, peristimulus. These pictures are the activity, right? These pictures are the activity. What do cells look like? Well, there's a couple that I showed you. That's that V1 cell. That's a classical Hubel-Wiesel simple cell. Neil Stryker got really famous on this. Hates high frequency gratings. Oh, these 6 tuples that I'm going to use to display things are 6 tuples based on these stimuli. So low frequency, high frequency gratings, low frequency, high frequency gratings. This V1 cell loved low frequency gratings, hated everything else. Negative contrast flows, positive contrast flows, didn't like any of that, right? This is a retinal ganglion cell. Let me show a different one. Let me show, this is the one I just showed you, right? It had this pattern to the low frequency gratings. It gives this pattern to the high frequency gratings. Gives no response to the negative contrast flows. gives a beautiful response with a strong initial transient to the positive contrast flows. Here's another cortical V1 cell. No response to low frequency gratings. Orientation, beautiful orientation tune, complex-like response to high frequency gratings. 3-dot negative contrast flows and 3-dot positive contrast flows. No response to, all right, what's going on here? Distinct responses to different stimuli as Toby properly characterized it, really complicated, okay? Let's build our manifold and see what we get. First question is, how do we build the manifold? The game is we have a whole bunch of neurons responding to this ensemble of these crazy stimuli, and we have all the responses in time, okay? What we want to know is, since each point on the manifold is a neuron, nearby points should respond similarly to similar aspects of the stimulus ensemble in time, right? How do you define similarity? What does that mean? This is the key question in manifold inference. It's a key question in much of data science, but it's a key question in manifold inference. So here's a cartoon of why that question is interesting, right? Here's a collection of neurons that Mike actually recorded from. And you can see that neurons I and neurons K love low frequency gratings in a similar way. They hate high frequency gratings. Well, they get this transient response and then a little bit of a linear response to negative contrast single dot flows. Also to oriented ones, nothing to these positive contrast flows, right? So neurons I and K look really similar across our stimulus ensemble. So on this manifold, you'd expect neurons I and K to be close to each other, right? Whereas say I and J, look, J gives this transient response to high frequency. J gives this transient response slightly delayed. This is why it's not just a rate code, because we have the exact timing. Slightly delayed to the positive contrast flows. So neuron J is going to be far away from I and K on the manifold, okay? You get the idea of where we're going. Is that clear? Because it gets a little technical in the next couple of slides. It's just pictures, but they're actually a little bit technical. So how do you define similarity over this ensemble of these crazy PSTHs, right? That's the question. We're going to do it in 2 stages. In the first stage, we're going to express the neurons as a function of their responses to the stimuli. We're going to express the neurons as a function of the responses to the stimuli. In the second, as we're going to define a similarity kernel over these responses. Okay. So how do we?
Is this always PSTHs, or are you doing single trial dynamics?
No, we could do single trial. We started out doing averages over 10 trials, and we never changed because it didn't matter if we did one.
I see.
Okay. Yeah. So let me warm you up with the algorithm on a toy problem. Okay, here it is. My evil student Luciano has a secret model for this recurrent network. You see this secret model? He feeds it a bunch of stimuli at these different orientations. And we know these cells are orientationally selective. We don't know who's connected to whom. We get this data matrix. What we would like to do is infer some kind of manifold that says, how are these related? Many of you will notice this is a ring manifold. And you'll say, remember, I and J were really similar. You're expecting them to be nearby on the manifold. K was really different. You're expecting it to be far away on the manifold. Okay? So how do we do this?
So what is the role of the circuit? I mean, in the left picture, every neuron has a preferred.
Forget that. Yeah.
No,
every neuron here has a preferred orientation. We don't know it. All we have is the stimuli and the responses.
We don't actually have a circuit. You just have neurons.
That's right. That's right.
Okay.
Yeah, this is unknown. Remember, this is my evil student, right? He did this at night. everybody was asleep. We don't know what he did, right? We're guessing he had something, but we don't know. We don't know. Okay.
Then you get a degree.
Why did this meeting is being, okay. Express the neurons as function. I don't know why it stopped working. Okay, so the data that we have is actually a tensor. And the way to think about it, remember, each neuron gives a response to each stimulus in time, okay? So in this cartoon model here, every neuron has identical dynamics. So we don't have to worry about that. It's going to make life simple. So how do we think about this tensor? Well, the natural way to do so is to do a non-negative tensor factorization of this data. And what will that do? It will tell us, for example, these neurons here like this stimulus, and they have that temporal response. Okay? You see what's going on? The next factor will say these neurons like this other stimulus, and their dynamics are the same, but that's because this is a really toy model. Okay? Dot, dot, dot. There's a whole bunch of these factors, and they separate out which neurons care about which orientations and the response in time. So you see that? Do you see what the factors are? So now if I look at this, what's this factor, right? This factor is a measure of the response of all the neurons to this stimulus over time. So I can take these components, these factors, these components of the factors and arrange those into, where'd it go? Arrange those into a linear space. And so this vector goes here, this vector goes there, and it's very much sort of analogous. It's not identical to, but it's sort of vaguely analogous to the way you string up eigenvalues in that sort of analysis. So this gives us a linear space in which we have neurons by factors. And it's in this space that, if we view it geometrically, neurons that are responding similarly are going to be nearby each other. So we define our kernel in this neural space here, and I call it the Ian kernel because this by itself was a 1.5 year technical problem. And the reason for that is related to the slide you had with Tisney and all that other stuff, right? Yeah. The problem in what people normally do is they either build the data graph underlying manifold inference as connecting each point to its k-nearest neighbors, or defining an epsilon and connecting it to all the points within an epsilon ball around that. Those are the two things that people do. That works if and only if you know the dimension of the manifold and it's pure, right? These manifolds are non-pure. In fact, every manifold we've ever encountered in neuroscience is non-pure, but that's a different issue. So we have this way of saying the neighbors of one neuron are well-defined. The neighbors of some other neuron in its neighborhood are well-defined. They may not be the same, right? The Ks may not be the same for those. That's a separate talk, okay? You then build the data graph. You then build the manifold. We use diffusion maps, and that's a whole other thing, but it's a Yale product. So there's Laplacian eigenmaps, diffusion maps. We think they're the best, but we can all argue. And this gives a manifold from those data, which is this ring. And the manifold was, in fact, built on Sompolinsky's ring model for visual cortex that says neurons with nearby orientation preference excite each other, neurons with different orientation preferences dislike each other, okay? I'm not going to have a chance to talk about circuitry here, but there's something very deep that I just want to say, and that is the relationship between the structure of this manifold and who's connected to whom. So if you look at that tangent space to the manifold, it indicates in an exponential neighborhood. The tangent space of the manifold tells you which neurons excite each other. Tangent space of the manifold tells you which neurons excite each other. I'm happy to talk about that offline, but I'm not happy to talk about it now. Okay. So what does this actually look like for our mouse visual system? Here's the retina.
But can I ask like how this compares to other methods in terms
Yes.
of performance?
Yes, you can at the end of the talk.
Okay.
Okay, so here's the manifold for the retina in diffusion coordinates. As it rotated, I hope that what you saw was it was super clustered, and there were all these clusters that we could easily define in the structure of the retinal manifold. And I just go through, here's a bunch of them. Remember, each point on this manifold is a neuron, and nearby neurons respond similarly. So there's a neuron. Here's its response to our ensemble of stimuli. Okay? It likes low frequency gratings, high frequency gratings, hates negative contrast, loves positive contrast. Look at that. I mean, it's cooking, right? It's cooking. And there's a nearby neuron to it. Its response structure looks basically the same. Basically the same. I got to speed up.
Other than the convenience of PowerPoint, why is this in 3D?
Well, just because we can rotate this around and
That's okay. That's okay. That's okay.
I can tell you what it really looks like, and the delicate issues of how do you define clusters in a 6-dimensional manifold, blah, blah, blah. That's offline stuff. That's technical.
But also, there's you're not doing anything weird there. Just the usual stuff that you've been doing for a while there. So
We're not only not doing anything weird. I think we're doing more tests to make sure that what I'm telling you is true than anybody.
I might trust you anyway, but I just want to know.
Yeah.
Your usual thing there. Okay.
Yeah. So we go to a nearby cluster. Look, this pattern is completely different, right? So as we go around the retinal manifold, we see these clusters have all these different patterns. Whoops. All these different patterns. Okay. Turns out each of these clusters is a well-defined retinal ganglion cell class. Okay. So from this perspective, we get a neural encoding manifold. What does it say? The neurons are highly clustered with one another. The clusters correspond to categories of retinal ganglion cells that the neurophysiology community has figured out over the last 30 years. Okay. So basically, this is reconfirming what's already known. From a machine learning perspective, this says, well, maybe the retina is more like a dictionary than a network. That may make some sense to you. I don't know.
But I mean, the classic way to identify the neurons is kind of the same. Like you show different stimuli and then you cluster their.
I didn't do any. I didn't actually do any of the clustering as in the classic. I know the Thomas Euler papers and stuff that referred to. We did none of that. This was all done by building this manifold, right? We just randomly chose the stimuli based on the arguments at the beginning. We did none of the designed clustering analysis that's in their paper. We just built this manifold, right? You don't even need to describe it as clustered. You can only look at neighbors. And remember this, somebody over here asked about geodesics, right? So if you walk along this manifold, you walk from these neurons, you're seeing a whole bunch of PSTs that look like this. You cross over, boom, suddenly you see a whole bunch of PSTs that look completely different, right? So trajectories on this manifold are non-smooth. And that's in effect a definition of clustering. Yeah.
I think you actually just answered the question, but the neurons between clusters, so if it's non-smooth, you're saying that.
Right. So who are these guys here?
Yeah. Are they a combination of, or are they totally something else?
Yeah.
Or are they just outside of neurons?
Yeah. So I'm gonna make a couple of technical comments. We find based on Greg's so Greg excises the retina, places on his array. There's a particular spacing of his array. So his array is particularly accurate at sensing about 20 retinal ganglion cell types. Cells that are too small tend to fall through the cracks, et cetera, et cetera. He also may pull out a chunk of retina and place it down in a way where we're missing a bunch of the cells. So we think these guys in between are either the classes that are not well represented or the classes that are not well sampled. I can't prove that, but that's what we think. Well, what I can prove is for every natural cluster that you find, we didn't do this. We gave him the numbers of these neurons. He then went and did the kind of analysis that you're referring to from Thomas Euler, because he has that data in his lab. We didn't have that data. He's the one who said, oh, these are off-sustained, these are looming, et cetera. Yeah.
You made a comment there about this having sort of a two-way aspect. Can you elaborate on that?
Yeah. So
you're talking about pattern detection, recognition.
No, I'm not talking about pattern detection or recognition. I'm talking about lifting the image structure into a high dimensional space that's spanned by the parameters of these different classes. Right? In dictionary learning, that's what you do, right? You find a basis for representing.
You represent something like
your stimulus.
repeating
Yeah.
strike patterns.
Yes.
Have you read the books by studies by Barton on I'm going to give the name of the book, but he did exactly the same thing with humans, looking at black-white patterns and the sample number of them for the field of vision and what was recognized, what was not, and frequency as well. So you've done all the spatial stuff, but what was really interesting was the contrast sensitivity and time.
Yeah, so these are all drifting stimuli, as I showed in that example. And let me just comment on the implication about looking at the stimulus in time and whatnot. We work really hard to design these stimuli because we don't know where the receptive fields are for the neurons that Greg is recording from. So we needed the stimuli to have certain guarantees on homogeneity in spatial distribution and in frequency distribution. So we have all those guarantees for that. So we worked really hard to factor out all the positional effects and those other things, which would be extra dimensions in the structure of this manifold, just because to do that, the data you need goes up exponentially. And we had a few thousand cells is all.
Wait, can you explain that? How do you factor it out?
So that was the design of the stimulus. So
like the spacing between the dots and
the spacing between the dots and all that. And so that's a side technical discussion. But we didn't want the location of the receptor field to be one of the key dimensions of the.
But was it empirical where you did it, you calibrated it and then tested it, or you used, let's say, a model of these cell types and designed this thing?
Oh, no, we designed the stimulus so that they were approximately constant in contrast, frequency, et cetera, across the display.
And across the retina, which changes the scale of the receptor fields. Right?
That's correct. Yeah, all that stuff. Well, they're constant across scale, across position, and across time. Yeah, and frequency. Yeah.
In the end, are these like Gabor?
No, these aren't. Remember, retinal ganglion cells are the Mexican hats.
Okay.
Yeah, these aren't anything like Gabor's. Yeah.
I guess like a developmental question. Are these like genetically encoded or are they learned in some way?
So yeah, that's a little bit outside the context of this talk. Much of the structure of the retina is genetically encoded, I believe.
I would say it's about 100%.
Yeah, I would say most, because there are, everyone thinks of the retina as this feed-forward system where you go from photoreceptors through a few neural layers to the retinal ganglion cells. So it's a very feed-forward kind of model for things. But there are these amacrine cells that provide interaction terms that, yeah, the story gets to be a little bit more complex.
As usual, Michael's understating things.
No.
Can you get more than less? I'm just kidding.
Let me not dwell on that question because I want to go to V1. Okay, I want to go to V1. And so what does V1 look like? So V1 is a completely continuous manifold. It looks nothing like the retina. And if you look around it, you see, it was really, where's that? It's a really continuous manifold. It's got this crazy arm sticking out the side. It's quite beautiful. The non-pure aspect of the manifold is this arm is lower dimensional than the body of the manifold here. So you really should think of it as the conjunction of several things, but that's the V1 manifold. How do you look at that? Well, you could start at a particular neuron. That neuron over there is one that likes all the stimuli, gives a transient response to some, gives an orientation tuned response to some, but it's a pretty crazy guy.
When you say lower dimensional,
sorry?
So you said this arm is lower dimensional than the other. I mean, I guess in this three-dimensional picture.
Oh, you can't see that. Yeah.
But so how do you know that?
We have dimensionality estimation algorithms that work off the data graph underlying this manifold, and they're very accurate. And I'll talk to you about that after this. Yeah, I'll talk to you about that after this. But
But there could also be 3 and 4 dimensional structure because you don't get this here, but you get 2 to 3.
No, this is just a projection down. In the full structure of the manifold, you have to work with the data graph, and because there you know who your neighbors really are.
But you'd have all sorts of possibilities of having 5 and 6 and 4 in there, but you just now you're down in 2 and 3 and.
No, we're projecting this down to 3 dimensions, but I should not.
So a 2-dimensional one pops out in the 3-dimensional projection.
Yeah, well, this actually is closer to a 3 inside a 6. Yeah, but that's the way to think about it.
Okay, that's what I was kind of asking. Is it really 3 and 6 and not? Yeah.
Okay. It's really closer to 3 and 6, and a little bit of a boundary condition.
And is the 6 a factorization of that 3 and something else, or?
I'm going to elaborate on that a little bit. You're going to get a little bit of understanding of the 3. Okay, so let's walk across. So this is a continuous manifold. So now taking a geodesic walk across the manifold makes sense. And so as we walk across, we can look at the PSTs for the neurons that we encounter as we move along. So you see, as we move along in this direction here through these various neurons that are highlighted, I don't know if that's green or yellow, you can see we go from this neuron over here that's completely promiscuous, likes everything, down to this neuron over here that only likes gratings, right? As we get over to this corner here, it seems to be something that likes gratings. Right? We can take other trajectories through. If we go in a completely different direction, it continues like everything but low frequency gratings, right?
Sorry, just so I understand, to get down to these 3 dimensions, you're doing what, like an ICA on top, or?
No. These are diffusion maps, and so we're looking at the most significant diffusion coordinates.
Got it.
Yeah. We're actually looking for coordinates that are not redundant. So the most significant, not redundant coordinates.
Okay. No, thanks for.
Yep. And so here's a kind of snapshot. The manifold now got rotated around. So the arm's over here. Okay. So the way to think about it, look at this arm. This arm only likes low frequency and then starts to mix in other gratings. This arm is the stuff that Stryker's paper talked about. The rest of the manifold is much more richly structured. Look at you can kind of see a gradient of the PSTs as you move along. The guys on this side, these guys over here, they like everything. They're fun. Huh?
Or hate it.
Or hate it.
Yes.
Well, you're exactly correct. As a matter of fact, yeah. So
it's very high frequency too. I mean, so but so what is this? I'm trying to think about what's this versus this now, back from the time and space, right?
What? No. So this is direction.
Yeah.
And time.
Yeah, time.
This is low frequency gratings, high frequency gratings, negative contrast, positive contrast flows. Okay.
I have no short-term memory.
Yeah, I know. That's why I'm reviewing it.
Thank you.
Yeah. You're right. So yeah.
So for old folks, you could just have another little thing that shows.
In the paper, there's all stuff it's documented, and if I were an honest lecturer, I would have had more updated figures.
So there's a real important lesson here, which is that the field had spent most of its time with stimuli up there and only saw those low frequency responses, right?
Yeah. So some of these neurons over here, they still like gratings.
Oh, yeah, no,
over here. Yeah,
it's a
but
spectrum.
some of these guys don't like those at all.
Yeah, but the spectrum, but also there are some cells that really like high frequency. They're not blind.
That's right. That's right. And back. Yeah, Andy. Yeah.
I was just gonna ask you if you know anything about the spatial arrangement of these neurons with respect to this manifold structure, or if you know about how they're.
We know, we've studied in great detail their layer arrangement, not their spatial arrangement. And I'll come to that just for a drop. Yeah, Bobena.
So, I mean, can we think of the high frequency responses that's coming from these subunits that are not excited?
Absolutely, yeah, that absolutely. So right, so one of the take homes from this, which I would never say in public, stop the recording, right? Is the receptive field model, the linear receptive field model makes absolutely no sense, right? The other takeaway from all this is these neurons are all sitting in these in vivo networks. They're all working together. None of this is individual neuron stuff. None of this is individual convolution like stuff. They're all in these networks in visual cortex, right? And that's why this continuous structure of this manifold is so beautiful, because it reflects that circuit property.
So you should not think of this as some sort of a simple signal decomposition in some bases or something.
Yeah, no. So I think that was why I made the comment partly for you about the retina. You can do that in the retina. The bases are hardly orthogonal. They're more like independent components or something like that. They're hardly orthogonal. You can't do that over here. You cannot do that over here. And that's the key point. So what you would like to know is, instead of some basis for this manifold, because remember, this is a really high dimensional space. This is the outer product between all the stimuli and all the possible responses in time, right? You saw how crazy those are. And this is the organization of that. So these are all the stimuli in time.
Where is sparsity?
Sorry?
So wouldn't you think that things want to be sparse in their representation?
So these are the neurons that are active to those stimuli at that time, right? So we're not seeing the ones that are quiet. We're not seeing the ones that are quiet. I have a lot to say about sparsity, but it's not so apparent in this representation of the manifold.
In other words, I'm sorry. In other words, there may be other stimuli you haven't thought of yet that could make the ones that are silent active.
That's correct. That's correct. And so another way to put that is the structure of this manifold is a function of this ensemble of stimuli that we're using. Yeah, that's absolutely the case, right? So I got him. So you could say, oh, well, Zucker used a different ensemble of stimuli within your here. Yeah.
You started sampling from the null space of that stimuli?
The null space of which stimuli?
The stimuli that creates this manifold.
No, that's infinite dimensional. Yeah, no, we don't know how to sample from that. But the last part of the talk relates to your question. So put that on the stack for a second, okay?
So what percentage of the cells do you characterize?
Let me put it like this. When Michael did these experiments, he would insert the electrode using their gratings. They would get 20, 30 neurons per probe. There's 125 sites on the electrode. He get 20, 30. Using our stimuli, he gets 80. He would get more if spike sorting were better, but that's another.
How many neurons are within range of those electrodes, just based on the anatomy? How many pyramidal cells?
Yeah, probably many more than that.
Yeah, tens of thousands. Right?
Yeah, many more than that. And there's a delicacy. So you commented about neuropixels and whatnot. There's a real delicacy on the technical side of getting these data. Mike likes this tetrode these tetrode electrodes with 125 sites that somebody at Santa Cruz builds for him, because they're really thin. And he thinks when they insert them, they're doing much less damage than the neuropixels, which are an order of magnitude bigger. And he's very nervous about using those. We're going to neuropixels because there's no option in the field. But yeah.
Yeah, but I mean, it is worth pointing out, electrodes all have like a recording bias. They tend to get the cells that are bigger somas and especially cells that require more. So
All that's true. And that's exactly the recording bias I talked about in Greg's stuff from his multi-electrode array. There's undoubtedly recording bias here. Nevertheless, we think this manifold is not uninteresting. And
Have you tried this with the most exciting stimuli data sets from like Andreas to Leas, where they figure out?
please be quiet.
But it,
Please be quiet. Please be quiet. So given that we have this manifold, one thing that you could do, we did not use Andreas's, but I'm going to talk about Allen data in a minute. So you can paint this manifold with various functions. So you could paint it with a function, for example, does it prefer low frequency gratings or not, right? You could paint it like that. And this is how you see that arm sticking out here. You can paint it with lots of other functions, low frequency versus high frequencies, I like gratings versus flows. This, you can start to infer all kinds of physiological properties from this. I got to speed up. So the putative inhibitory neurons are these guys over on this side of the manifold. Remember, they're the ones that liked everything. So that would, Mackenzie, that you were dead right? These are the inhibitory interneurons. They go to one side of the manifold because they have very different stimulus preference properties than the excitatory neurons. This low frequency arm over here is all excitatory neurons. Yeah.
How do you know what is spiritual, what is excited?
So we don't, but Michael knows because he did the recordings, and so they do narrow and broad spiking analysis. We didn't do that. We are simply painting his results on our manifold. Okay, so just in the same way that Greg did the typing and the array layout, etc., the retinal ganglion cells, Michael's group did broad spiking, narrow spiking, etc. analysis. Put it on there. We can do all kinds of layer analysis. I could talk about this for a long time. Why would you expect this topological diversity to arise? I'm just gonna whip through this really quickly. It's a technical point. If you have a densely connected network in our manifold, it's going to be a very tight, pure, continuous closed manifold. If you have multiple of these and they're different, they'll be in different spaces, in different portions of the embedding space. So that would be a discontinuous manifold. As you allow some weak interactions between these discontinuous pieces, like say the amacrine cells in the retina, you're going to get some connections between them. We think this is really what the retina manifold.
Wait, but it doesn't sound. But they could be decoupled circuits, but because you present the same stimulus, they look like they're connected.
That's correct.
No, like you. So it's not. It's not. This is not an anatomical picture. It's a functional.
This is everything I'm saying. Everything I'm saying is functional. Everything I'm saying is functional. I'm not saying
functional.
Yes, that's correct. I'm not saying anything about anatomy.
Right.
Yeah. Right. And of course, if you allow it to be richly, strongly coupled, you get these crazy continuous manifolds, maybe non-pure, et cetera. We think that's cortex. Okay. All right. Here we go. Right. This is your chance to participate. Right. So we know something about the population organization of retinal ganglion cells. We know something about the population organization of visual cortex. What about your favorite deep network? Okay. Here's a forced choice you have to make. Do you think these are more like this or more like this?
Which layer?
No, of course, more like the right.
You can choose your layer. Huh? Of course, retina. Of course, retina. So we have an outspoken opinion from here at all layers.
Well,
Who thinks it's more like what?
The outspoken critic to my left says, of course, retina.
Well, per layer, I would say yes.
Huh? Per layer.
Yes.
Wouldn't it be like the convolutional layers be more like the retina and then the MLP at the end be a lot more like very single features?
Yeah, so that's possible. Yeah, Corvetta, what do you say?
Retina.
Yeah, you guys are terrible. So the first thing you have to ask is, does it make sense to even ask this question? Because, so I'm gonna give you the answer for ResNet. We did a half a dozen of them. I'm gonna give you the answer for ResNet, right? So what's ResNet? Well, you train it up with all these ImageNet things, you feed them through, you look at the activity across layer, and what's the output? It gives you a classification for each input image, right? That's a game we all know. Well, what happens if we feed ResNet our lunatic ensemble, right? Well, ResNet's happy as a lark. Look, it's firing the same way it did for ImageNet, and it happily does classification. It says positive contrast flows are spider webs, 93.5. Okay. If we build that manifold.
Wait, sorry, this is a pre-trained then ImageNet ResNet backbone.
That's correct. Yeah. We're not doing any training there. Yeah. If we. Sorry. Was that a phone? Yeah. If we build the manifold, boom, it turns out it's got very interesting properties. The reason why Jim DiCarlo and those guys think these are models of the brain is if you look at a particular neuron and you look at the PSTs, look at this. You get excitation to some of the patterns, not all. You get these beautiful orientation tuning curves, etc. Right? Hey, these are neurons just like the brain, right? What they don't realize is, what they don't realize is this manifold is completely discontinuous. This is more discontinuous than the retina. The reason for that, of course, is weight sharing, because it's all these distinct convolutions and feed forward, right? So it's a directed acyclic graph. There's no interesting interaction. There's nothing to make the manifold continuous. If you take the cells in these different clusters that you get the same kind of tiling of visual space that Greg found for retinal ganglion cells, so on and so forth. That holds all over the place. You get all these beautiful PSTs. So DiCarlo would say, oh, look, it's a brain.
Where's time coming from?
Sorry?
Where's time coming from?
So we took our stimulus and moved it across and reorganized the output of the units in the different layers so they would look like the temporal response that we got in the network. Okay?
Concatenating over time.
Yes.
So what did you do? Take a video CNN?
We didn't do it.
Wait, so how are you defining temporal response for
The temporal response for we're drifting the images over position in different directions.
And you record
like that, and we're recording. We're taking the units and mapping them into the same scale as the neural responses. Yeah,
actually same as in the experiment.
Yeah,
same.
Yeah, it's exactly the same as the experiment. Yeah, you're exactly right. And it doesn't matter which layer you look at.
Yeah, of course.
And it doesn't matter if you look at the output layer. It's all incredibly clustered. And you'd want the output layer to be really clustered, because if you think of the discrimination problem, you want it to be clustered, right? So that's point number one. Okay, so I promised Terry some new stuff. Can I go for another 5 minutes?
Yeah. But leave 15 minutes over.
I know. No, we started 10 minutes late, and then Terry gave a 15-minute intro.
Keep going.
I'm happy to end here. Yeah. So,
Steve, no one's got another appointment.
Anybody who wants to leave.
So many of the people here think, well, Michael Stryker, who's he, right? Greg Field, who's he, right? Let's go to real data. So what we really wanted to know are the manifolds, the neural encoding manifolds for the higher visual areas continuous like V1, or are they different? Do they have interesting topology? So we went to the Allen Institute, where they recorded from a collection of higher visual areas. And I have this figure from their paper that shows, you see V1's kind of surrounded by it. And it's sort of like V1's kind of surrounded by all this higher stuff in the primate, the picture everybody knows and loves. And the Allen data consists of two sets. One, gratings, either drifting or flashed, and the gratings span the frequency, spatiotemporal frequency coordinate that it's thought mouse cortex cares about. And the same number of images randomly sampled from, not ImageNet. Who's the guy in Holland that so these are Van Hatteren. So a bunch of natural scenes, and there's the frequency response. And the key point is that look how the frequency response drops off. This is the log of the magnitude, but this is the plot you always see, that there's lots of parts of these images that are carrying low frequency content, not so much high frequency content. Keep that in the back of your mind, because this part of the talk I don't really understand, okay? So the Allen people, they have many more students than I do, and the connection map is a mess. They really want to say, well, there are these different streams. There's the dorsal stream, the ventral stream, all these ideas that are inherited from the primate. I'm not sure I see a dorsal and a ventral stream in here, but they managed to hallucinate one in there. So we thought, well, we'll look through their data. We'll see if we can find it. The short form of the answer is, well, we didn't. But we did find some other curious things, two of which I really don't understand, and I'm going to tell you about. One, so here's the manifold for, so the Allen people call V1 VisP, primary visual cortex. This is the manifold based only on the spatial frequency data, on the grading data. And you see it's beautifully continuous, okay? This is a composition of the drifting and the static grading. And you can see, if you sample from a bunch of neurons, you can see you get all kinds of stuff, right? You get tightly tuned orientation, complex cells, you get broadly tuned stuff. And you see it's kind of tuning with coordinate going across the manifold. If we plot on this manifold the orientation selectivity index from the Allen Institute for these neurons based on the spatial frequency data, you say the really tightly tuned ones are over here. That's these guys, they're really tightly tuned. And as you drift off this way, they become less tightly tuned. Well, yeah, we agree with that. That makes perfect sense. Here's another one. If you plot the firing rate, because you would think firing rate, remember, since we're looking at these PSTs as a key part of the organization, that firing rate would be a key part of the way these neurons are organized. And indeed it is, right? Low to high frequency as you move right to left across the manifold. So these are a couple of interesting coordinates. And notice, yeah, that these are not orthogonal coordinates on the manifold. That the stuff that's really singing is probably inhibitory, because they respond to all sorts of things. The stuff that's really well tuned is responding a little bit less on average, but you can read that right off of these PSTs, right? You can read that right off. So I haven't told you anything you shouldn't have expected. Yeah.
Data set calcium imaging?
No, this is neuropixels. Yeah. They have calcium imaging stuff. We didn't analyze that yet. Remember I said over here, the natural scenes are too complex to analyze. That the dimension grows without bound. So we tried plotting all kinds of properties of natural scenes and found this one. The log of the ratio of the mean firing rate to natural scenes compared to static gratings, right? It's unbelievable. Gives this beautiful function across the manifold. This is V1, right? Gives this beautiful function across the manifold. And you can see, we were thinking that, well, the natural, what does this mean? This is the average. Basically, I could show you the max as well, and you get the same plots. So I just made these with the average this morning. I maybe should have done the max, I don't know. But what does this mean? It means for certain neurons, there exists a natural scene, regardless of where its receptor field is, there exists a natural scene where it fires better than it does the gratings. Whereas for some neurons, regardless of where the receptive field is, regardless of what the natural scene is, it likes these gradients better. Okay, and I need to say for this, we're comparing the flashed natural scenes to the flashed gratings firing rates, so that we have exactly identical experimental paradigm for gathering the data.
What about the natural movies?
Sorry?
What about the natural
We didn't
movies?
do those. Yeah.
But did you find something that correlates with this axis in the gratings?
Wouldn't that be interesting? Yeah. So here are the higher visual areas, with the possible exception of VisRL, which is quite curiously the worst of these. They all exhibit a really nice coordinate that separates this ratio one to the other. And notice, as a corollary to this slide, you say, aha, well, the higher visual areas are also continuous. And so that's what this all started out to look at, but I didn't want to go there.
So RL is also what a lot of people call parietal cortex.
I know.
Yeah. So it's not fair at the visual area.
Yeah, isn't it curious
Yeah,
that
we seen the same thing with the natural movies. It's
Yeah.
the lowest by far.
Yeah. It's really
It's really an outlier.
It's an outlier,
Yeah.
but we didn't know anything about this. This is just data. So we started to look at whether there's a dominance of natural scenes to gratings by layer. And this is for you, Michael. I really don't understand this. Natural scenes dominate. This is V1. Natural scenes dominate across all layers except for layer 6. Where gratings really dominate, right? That holds true in all the higher visual areas, but only weakly for RL. But but all the other high visual areas. So I think this is possibly not irrelevant to your thinking about corticothalamic loops, in the sense that we were really betting that every layer is going to prefer some natural scene, because this is the mean, this is the max. So you see the two columns here, and the reddish stuff is natural scenes, the bluish stuff is gratings, and we were really betting it's going to be all red, but it's not. It's not. Why would layer 6, which feeds back to the lateral geniculate in the thalamus, have this preference for these gratings, these elongated orientation-rich patterns? That's a puzzle to me.
Okay, well, here's the hypothesis. We know if you actually record from single neurons, and this is, I know it's true in V1, but I'm not sure if it's in higher. What you find is that compared to only giving a simple stimulus like an edge or a bar in the receptive field, you get a much higher firing rate than if you give a natural scene. And the reason is that there's something called a non-classical receptive field, which is when you stimulate outside, you don't get any response to the neuron. But if you have a response to a stimulus in the receptive field, the outside will modulate that firing rate. And that's I think it's found all over, right?
Yeah, for sure. Yeah, surround.
So what you're doing, I think, is showing that the layer 6 is probably doesn't have that lateral interaction. I call it the spatial context.
Yeah. That may well be. Layer 6 also in primates has the really largest receptive fields. In our model of end stopping, we use it to build up the surround, et cetera, et cetera. There's a million things about layer 6. Question is, what about the projection back to the thalamus? Because you would expect the thalamus to be caring about some interpretation of the information coming from the retina up into layer 4. And many of the theoretical ideas, I know, Michael, these aren't consistent with your thinking, but many of the theoretical ideas say, oh, these Mexican hat-like receptive fields are decorrelating the data. And that's the heart of the population comment I made the other night, right? So if you're doing all this work to decorrelate the image information to load into the retinal ganglion cell dictionary, why do you feed back this highly correlated information?
So there are papers out where people have given different stimuli to layer 6 cells. So you just have to, you know.
Yeah, the problem is we need to look at mouse. Yeah.
Well, mouse, yeah, but it might be different, you know.
Yeah, I don't know. So this, yeah, Michael.
Can you give me my guess?
Yeah, absolutely.
Okay, so
this slide is for you,
yeah.
actually.
Okay, so my kind of hypothesis about the neocortical microcircuit is that layer 6 is trying to predict the next input to layer 4. For kind of a variety of reasons that would be a long argument. So I don't know, it's kind of consistent. The gradings are more easily predicted.
Yeah, maybe. I don't know. These are just what the algorithm says from the data. Yeah. Okay, go back to your question. Is there some relationship between all this frequency stuff, which, you know, we built these manifolds just out of frequency, but they have this beautiful coordinate about the ratio to natural scenes, right? What could that mean? So first thought, everybody would think of this, right? Natural scene statistics, right? We know the brain's wired up to reflect natural scene statistics, of course, right? Every area has more noise, prefer low frequencies and high frequencies, boom. And so this is the plot of that from the Allen data, right? And boom, you say, yeah, look at this, right? Here's to give you a feeling for what these frequency bands are. Here are some examples from the Van Hatteren database. That's the low frequency filtered version. That's the high frequency filtered version. These are the 3 intermediate frequencies averaged together. Okay, it's a broad frequency, right? Sorry, a broad bandpass filter for the intermediate frequencies. Okay, so there's lots of theories in computer vision and cognitive science, right? The low frequency stuff gives you the gist of a scene. Boom, O'Deliva, Tony Toralba, all those guys. Boom, low frequency, gist of a scene, right? Boom, low frequency, it's a face. Boom, low frequency, he's smiling. Well, low frequency, boom, she's frowning, right?
No.
I don't know. What's the high frequency stuff? Well, yeah. Oh, that tells you, oh, this is a butterfly. It's not a blob, right? So, so you say, oh, maybe this is what it is and that's where it is. I don't know.
By the way, this is actually, Marge Livingston has analyzed the Mona Lisa in high frequencies and low frequencies. And if you look at them, you have a different percept of the expression.
Absolutely. Yeah, absolutely. Yeah. Okay. Here's the answer to your question. If you look at the response to natural scenes versus gradings per frequency band, for every area, you get this U-shaped curve. Natural frequencies are loved by the low and high frequencies, not so much the middle frequencies. Okay.
What are the axes?
This is frequency here.
Spatial frequency, right?
Yeah, spatial frequency. This is the ratio of the log ratio of, I think it's the max firing rate, but it might be the mean. I just can't remember. I didn't put it on the slide.
Right.
It's firing rate.
Heavy
Yeah.
tables, right? That's.
Yeah.
But the frequency, you take some statistics
Natural
from the
scenes
image.
have more high, low frequencies.
Sorry?
How do you get frequency?
We know the response of each cell to each image. So we calculate this, right? We know which cells are in these bands because the Allen Institute told us
When
what.
you have a natural image, what's the frequency?
Yeah. Yeah.
No.
I showed you some.
Frequency of the natural image.
I showed you some of these over here. Whoops, where'd it go? Right, maybe they're a little bit small. These are the natural images here. That's the modulus of the spectrum. That's the modulus of the log of the modulus of the spectrum.
Natural image has a power spectrum.
Exactly, yeah. And they all drop off like that. Yeah.
But
then how are you computing it against?
Just asking a simple question like that.
yeah, how do you decide what x coordinate to plot?
In this figure here, we have a group of cells, that's these cells, right? We have, this is a group, these are cells, this is, these bars indicate all the cells that the Allen Institute recorded from. These cells here give their best response to this frequency range, okay? Let's say there's 100 of them.
From gratings.
From gratings, yes. We take these 100 cells and we ask, what's this ratio for those? And we plot the average of that here, okay? We take these cells, we ask, what's the average? That's this point. We take these cells, what's the average? That's this point, etc. Okay? So even though there are fewer cells here, this curve goes way up because the average goes way up. Okay? So what does this mean? I don't know. But is this related to what I've been showing you? So if you take that and plot the cells that prefer the lowest and the highest spatial frequencies against the intermediate ones, you get the same distribution as we got for the natural scene spatial frequency function on here. I also don't understand this.
Well, one mystery explains that other mystery. Right?
Well, what it says is our manifold has revealed what I think is the first structural property on neurons in the visual system about natural scenes. Because as Mackenzie pointed out, that we're sampling in a crazy random way from this essentially unbounded space. And so we take these random samples from this unbounded space. Why would you ever expect to find any structure? Well, we found some. And our manifold tells you it has some functional relationship to spatial frequency of a sort that no one that I know of, this is not coarse fine, this is coarse and fine versus the intermediate. Right? What does that mean? I don't know what that means. But I can tell you that the manifold not only has raised interesting ways of thinking about the organization of cells, and as I made in that comment about the tangent space to the manifold, telling you something a little about functional circuitry, it tells you something about the function of the visual system to these stimuli that we really otherwise have no idea how to analyze.
So
yeah,
did Alan tell you how sparse the firing was in each area? Okay, that might be another factor.
Yeah,
That'd be implicit.
yeah, could be. We tried to compute a sparsity measure and check whether that tensor factorization, we couldn't get anything out of that. It took a long time to find this, actually. We tried all the stuff you would normally think of first. Yeah.
And is this during running or is this during when?
All of this is all of this is done with stationary.
No, but the mice are either running or not running.
Yeah, this is all non-running.
Okay, so
Yes.
you parse the data.
Yeah,
so
we
it's
parse all
only
the data.
non-running.
Yeah.
I see. And but eye movements?
We didn't, this is invariant, we didn't look at the eye movement stuff.
Yeah.
Yeah.
And so if you keep the natural scenes in there, then you get a discrete manifold.
No, yeah, we can't do it because the tensor factorization step doesn't work. Yeah, we can't do that. Yeah.
My prediction it's discrete and therefore it's actually a CNN. No, I'm joking.
Well, yeah, no, I understand. I would say that's a degenerate outcome of the algorithm, but yeah, Andy.
I just said, what does this tell you about the functional connectivity? Is it that?
Oh, this doesn't tell us any, yeah, other than it's likely the case that neurons that are near on this manifold, because they're responding similarly in time to similar aspects of the stimulus ensemble, are likely connected, just as they were in the ring model. Yeah, that's all I'm claiming here.
Okay, last question because we're late here.
I'll just throw out one comment that might be related to the cells that prefer intermediate frequencies for the grading probably have a much more linear spatial summation over the receptive field. And that's because, you know, if you map their receptive fields of the Bohr patch, like it's about the same size as these intermediate gradings. So that kind of suggests to me they have more linear spatial summation. And so I mean, certainly cells that prefer high frequency, you know, are going to have a lot of subunits or hot spots. And at least in that end, it maybe makes sense that they see more features they like in natural scenes than the gradings.
Okay, well, let's all sleep on this. Maybe we'll have more ideas in the morning.